Thanks for the questions on that. We'll see where everyone is. I do think you'll find that the more you're in simulation mode for MP3, the happier you'll be. Getting, in terms of that initial goal, of course, getting pass-through working is still very critical, and that should be your primary goal. And then that shapeshifter, which we'll look at the source for that today as well, that's pretty good. You get the shapeshifter working, that means you have the scalar uniforms working, that means you have those basic arithmetic instructions working. That's a pretty good sign. You've made really good progress. Once we move on to the matrix things for like the cube flyby example, it's not necessarily that much harder. Our assembler rightly or wrongly kind of serializes the math for it, but at the same time, it can be pretty hard to debug when things aren't working for that. You do have to go back for pencil and paper for that because you're doing a matrix vector multiplication. For cube flyby, at least, it has to be some sort of meaningful matrix vector multiplication, not just an identity matrix. But if it doesn't work, that's what I'd go back to. Go back to the identity matrix. You should at least be able to inspect the data and see it's an identity matrix. I did a matrix vector multiplication. Did my input and output, are they the same? At the very least, you can check there. But things like, is it row by row or column by column? That's actually not an easy question to answer because there's several layers where that transformation could happen of the matrix. It could happen in the application, depending on how that GLM library stores the matrix. It could happen in the driver based on how you decide to store that matrix. It could then happen in hardware based on how the assembly level we decide to serialize that matrix, and then your actual implementation, it could depend on how you're actually doing that operation there as well. So getting it exactly transformed, or the transverse matrix, is a very common thing. The results won't look good. If you take a regular model view matrix and transpose it, it's not going to look very good. So work with identity matrix, see if you get that working. Do things like scaling the inputs. You can just do 2 on the identity, on the diagonal, and you can do simple testing and then worry about getting that final application working. So pass-through is a sign that you at least have, and that's not trivial, that's a sign you have things hooked up properly for MP3. It's a good sanity check. Then the shapeshifter, which is just those scalar instructions, and we'll look at that today as well together. And then it's not necessarily, I wouldn't call it a stretch goal. I would like every team to get it, but understanding that next step is a bit of a step for the cube flyby in terms of the data, how that's being represented at all the layers from application to driver to assembly, then to hardware. There's a lot of places things can kind of go awry there. And to test it, you really have to just kind of go one by one and check your assumptions every step along the way. So it's also important we understand as a class, conceptually what's going on in the shaders. It's probably a little funny in terms of the pacing right now that you may know some of this information pretty well because you've had to kind of make heads or tails of the MP3 assignment, but that wasn't necessarily my intention. So I want to make sure we have a good in-class understanding of what's generally happening with shaders. There's no, way to do it better than to learn by trying, but I want to make sure we're all on the same page with regards to architecturally, generally what's happening. We'll still have more time to talk about specifics, and then how we're interfacing with it as the programmer, and as well as with the driver, and some of the limitations. So this was a slide we already talked about before break. Understanding the data, I think, is pretty important for shaders. Generally, everything is going to be a float in terms of the data type that you have here. You can have binary data, you can have booleans, you can have integer types, but generally, unless you're specifying otherwise, everything is a floating point value. And as a kind of first-class citizen of the language and the compiler support, you then have these vectors and matrices of floats. You can have fixed type arrays, so no real dynamic memory allocation there. There's no operating system running resident on the GPU or in the shader core, so it's really just compiler time things that you can assume. And then the 3 types of data are pretty important to wrap your head around. There's arguably a 4th type as well, but just talk about the 3 types of data that you have the so-called per instance data here. The other term, which is the input data, is what you'll see in the actual syntax. That is per execution of that particular shader code. That is going to be constant just for that one run of that code. So you have 3 vertices for a triangle. The input data is going to be different each time. The attributes, that's your per instant data. You are then going to have as a second class of data, you could call it the per fragment, you could call it interpolated data, you can also just call it like the post-rasterization data as well. It's different than what we otherwise would have for the input vertex data. For the vertex data, we as the OpenGL programmer are specifying those inputs. Here's my triangles, here's what I'm sending to GL draw call. You're directly specifying the inputs for your vertex shader. For your fragment shader, you're indirectly specifying your inputs, and that can be a little tricky to wrap your head around. You're indirectly specifying it because you're generating those fragments in the rasterizer. So you could argue that of all the fragments you have for a triangle, you're directly specifying maybe 3 of those fragments because those are the inputs on the corners or the edges of the triangle, the vertices of the triangle. But then all the rest of those fragments that you're processing in your fragment shader, those are post-rasterization. So they're still inputs. They kind of work in a similar fashion, but they're not inputs that you, as the programmer, have like direct control over. Writing a test bench for that's even harder than for that reason, right? You can test values, but you really would have to have the rasterizer in the simulation loop to guarantee these are the exact inputs that my fragment shader are receiving. So they're both inputs, but there's that interesting relationship, and I don't have a good flow chart for it, but it goes from program, that's our initial input, our OpenGL program, to vertex data, that's input to the vertex shader, to transform vertices, that's the output of the vertex shader, to rasterizer, which then provides the inputs to the fragment shader. The output of the fragment shader is also going to be fragments, but potentially transformed and modified fragments. Beyond those classes of input/output data, you also have the per batch or per frame or per scene data, and that is things that you would specify just once per set of draw calls you have for a given frame of your scene. The term, it depends on what version of OpenGL you're working with, the term we use now for that is called uniform. So you see that in your code. That is something you set as many times as just once per frame. So from your program's perspective, it's not exactly the same as being a constant. You still have to go and fetch it from data memory. One thing you have to watch out for is you definitely have to invalidate your data cache, right? I have this value that I'm specifying as a uniform in my vertex shader, and it's like that X offset, if you've looked at Shapeshifter. How much am I moving my triangle in the X dimension? I specify that once per frame. It's ultimately just a load instruction in my assembly code in my vertex shader, but it's a load to the same address. So it's loaded. The first time it's going to be loaded and found in the cache. There is no mechanism unless you build one yourself to then invalidate that cache. So you do have to do that yourself. But that's kind of the sort of constant data, or at least it's per frame constant data that is going to be the same for all the vertices or all the fragments that are being processed in that particular frame. That model of the data being very kind of tightly bound to the GPU is a little different from a programming perspective. I think if we start simple, we'll see how we can extend this concept to more GPU compute type of things, where the data is still bound very tightly to the GPU and the individual CUDA cores, but we can pass pointers, and it kind of gives us this kind of global view of data. The pointer itself becomes a constant. The pointer itself becomes like the per vertex data that we're passing in, but it's a pointer then, and then you can offset the pointer and do more random access of memory with the same looking kind of C-ish type of code that we work with our GPU compute these days. The main goal of the vertex shader is to do a transformation of our position. We provide an input position, which, if you remember, I kind of reordered the topics that we were covering here. We provide the position in this so-called world space. Here's where everything is going to be located. We then have to set up a camera. That camera is going to be dictating what our scene is going to look like. It's going to dictate what should be in the scene, what should be not in the scene. Ultimately, and we will cover the math of this, that is one big matrix that gets specified per scene. We specify all of our vertices. We also specify this matrix that we're going to then transform all of our vertices via that matrix vector computation. That is the primary job of our vertex shader. If nothing else, it is required to do that. Now, that transformation can be an identity matrix. And when we have our so-called pass-through shader, I don't think I have it open here, so I'd have to kind of go find it. But when we have our pass-through shader, that's effectively what we are still doing. If you recall, I don't have it open here, but if we call the syntax for the pass-through.vert shader we had, it would take input vertex and would set GL position to our input vertex. It would just copy the input to copy the input to the output. That is effectively still doing a transformation. It's just an identity transformation. It's not changing the values at all. But if we didn't have that line, if the vertex shader was just blank, or if it didn't set anything to that GL position output attribute, it would be a compilation error. Our code wouldn't run properly. We wouldn't get any output, no matter what else we were specifying in our OpenGL code. So we have as our inputs the attributes, and we've talked to, and I think we understand what the attributes can be. That's at the very least position. Color can be an input, as we have a red triangle we specified as red, or the color itself is something we then calculate via other attributes. We can do a lot of texture mapping at this point as well. And then you have whatever other uniform, other per draw inputs that we have here. At the very least, we're outputting that GL position and anything else we want the rasterizer to take care of. So we have input attributes, which could be a certain number of them. We have output attributes, which could be a different number of attributes. It could be more, it could be fewer, but at the very least, there's that one input and that one output attribute, which is, here's my position. And potentially transformed, potentially not changed at all here. It's executed only once per vertex, so in terms of the computational overhead of a vertex shader, it's generally thought to be less expensive than the fragment shader, which is executed once per fragment here. Architecturally, this is a pretty high-level diagram, but even when looking at hardware released in 2023, the difference is really just of scale, not of concept in terms of what's happening here. Your vertex shader or your vertex processor that's executing your vertex shader programs generally can be thought of as a straight pipeline. In fact, until relatively more recent evolutions of the vertex shader architecture, even this relatively small amount of control was something that wasn't really feasible here, and it was really a straight programmable, but really just a straight pipeline of fetch, decode, execute, commit, fetch, decode, execute, commit. Now there is support for some variants of control depending on what version of shader architecture and shader language you are supporting, but in general, and this is still very much the case today, you're going to have this so-called SIMD organization. I think I asked, and people were somewhat familiar with the concept before, depending on when you took 381 and who taught it and what was offered in that. The idea you have single instruction and multiple data. People sometimes conflate SIMD with vector processing, and there are a lot of similarities, but that's the same concept. As opposed to working on a single scalar data at a time, you're working on an array, a vector of that data at a time. That allows for a lot of benefits, right? For a single instruction, you're doing maybe 4 times the amount of work than you would otherwise be able to do in a single instruction by having an ALU that allows for that kind of parallel operation that you're doing here. The downside is potentially is if you have that SIMD or that vectorized organization, you need to have workloads that can take advantage of it. If you have this vectorized organization and all of your math you need to do is just scalar math, then you're kind of wasting your hardware, right? It's very inefficient. For graphics, that's never a problem. We have our vertices, and they have these RGBA components, or these XYZW components, or RSTQ components. We always have these 4 wide vectors as our inputs. So almost all of the math we're doing, unless we intentionally create kind of silly shaders like we have for MP3, almost all the math we're doing is already 4 wide vector math anyway. These 4x4 matrices, these 4x1 vectors, all of our math is, unless you intentionally create something to not do that, all of our math is 4 wide, SIMD amenable already. So even as you have these modern, NVIDIA and AMD architectures that have, thousands and thousands of these cores, and claim certain things about thread organization and how many parallel operations they can do, ultimately the underlying ALUs are basically these. Different data types are now supported, so they're not all having to be 32-bit floating point types. There's other data types it can support, but basically it's vectorized arithmetic units. Give me 4 multiplications at a time. Give me 4 additions at a time. Give me 4 of the other basic kind of operations we expect to have. This is not necessarily being shown here in this generic vector unit, but oftentimes architecturally there's then a split between there isn't really a good way to describe it, but just basic operations and more special operations. So a modern vector shader, a modern vector processor can handle both the stuff you would expect, I think, like multiplication, addition, and dot product and things of that. It can also support inverse square root and sine of a vector. It can do those things. It can't necessarily do them as efficiently as it's doing the basic mathematical operations, but in general, if the language supports it these days, If there is a function call you can do in your GLSL code, there is an assembly instruction that gets emitted for it, and there is then effectively some direct hardware support for those instructions. You may have seen this in other design trade-offs you've had to make in any architecture or embedded systems course. There's no requirement that just because you have this functionality mathematically that you have to have an assembly instruction and you have to have a piece of hardware that just does that. Modern systems make this trade-off between code, assembly, and then microcode in terms of how things are implemented. In GPUs, although not all of that information is directly public, depending on which GPU we're talking about, there tends to be a lot less microcode and a lot more just direct instantiation of the functions that you would need. So if there's a sign of X operation in your GLSL, and there is, you can do sign of your input vertex, there is generally going to be a piece of hardware here that can take a vector of values and calculate sign of X on them. Can't necessarily do it in one cycle. It might be borrowing components from other units and doing some transformations to make the math a little bit easier, but it's generally not the kind of microcode implementation that other architectures would use for their fundamental design decision there. Here's another view of what else is happening here, showing kind of the different units here, but this diagram's a little high level, and it shouldn't feel all that different than your 381 style pipeline here. There are some differences, and maybe in looking at MP3, you've started to sense a couple of those differences. How this per vertex input and per vertex output data is handled is potentially a fundamentally different thing. For us, it is definitely a fundamentally different thing. We treat vertex input and output data as different than any other arbitrary input and output data. Those are not handled via load and store. We could have made that our design decision, but we don't. We treat it as a physical pipeline, right, still, with an actual physical FIFO dealing with our input and output things. And so dealing with this kind of input data requires a different hardware interface and requires different instructions than dealing with just arbitrary data that happens to be in our memory. So you have both. You have both in FIFO and out FIFO instructions, as well as load and store instructions. There's no OpenGL reason that requires that. It made the design a lot easier to kind of scaffold up and build, and going from not having that to then adding that. Otherwise, a lot of things here should look kind of similar, although it doesn't show all maybe the connectors you would normally see in an architecture diagram. You're going to have a register file. It's going to be a vectorized register file where you can, in theory, read from 4 values at a time and not just a single value at a time. Because our ALU is going to be vectorized in that same way, you're going to want to have a register file that can read at the same kind of bandwidth and read 4 values and write 4 values here. You're going to have both your ALU as well as potentially a separate special function unit. For us, they're kind of one and the same, right? Because we're using a state machine implementation, or at least I strongly advise you to use a state machine implementation for MP3, where there's a decode stage, and then whatever math has to happen then has its own separate potential sub-state machine inside your bigger state machine. In a more advanced implementation where you didn't have just one of these things, you had maybe 8,000 of these things. There could be different design decisions made in terms of perhaps every one of these units has an add and a submodule, but perhaps the logarithm hardware is shared amongst units, because while it is important to be able to support logarithmic operations, it's not something you're going to need to do nearly as often as doing addition and subtraction. So there's different design trade-offs and different sharing of resources that I think are important. First off, it's not entirely public, how it's done in practice today. And for us, we only have one of these modules, so there's no real sharing to happen. So if we need to support sine, cosine, log, and just more advanced operations, we're going to build one of them. That's all we can build anyway, and we don't have to share it because there's only one such vertex shader. So this kind of shows that lack of sharing happening here as well. There's also this swizzle unit, which I think is possibly the most maybe annoying and or complicated unit that is different than a 381 style processor. That's just something that is a very common operation. So for the vector types that you have, you're going to often find that you want to just access those components within the vector. And syntactically, you can actually use array notation for that. Input vector of 0, of 1, of 2, of 3 will still work. So that kind of syntax will work. What this swizzle/masking operators allow you to do is to access multiple subcomponents at any given time, which is useful. and then also allows you to do it in kind of any arbitrary combination, which may not feel useful, and oftentimes the examples are kind of toy examples, but there's a lot of real scenarios in which you'd want to be able to access, for example, dot zzz, and treat that as a vectorized component that you would have there. So that's a slightly different unit. It doesn't do any actual math. It's really just a reshuffling of data that, given an input vector that has 4 lanes coming in, we have an output vector that has 4 lanes coming out, and there's, we could do the math, how many combinations there are potentially there, right? Because if there's 4 different components, there's 2 bits to represent each component, so 8 total bits, so there's, I think that's correct to say, there's 256 possible swizzle operators that you would have to be able to, in theory, support. But you don't have to support them all independently, because you take a look at the first component, take a look at the second component, the third component, and the fourth component, and then just grab those individually here. We could talk a little bit more about what happens in those swizzle operators and just kind of play around with it as well. So I think I talked about this. The major fundamental use of the vertex shader is to do that transformation from this world space to this clip space. We've covered clipping conceptually, we haven't implemented it, we won't be implementing it. Another way to think about what that transformation has to do is it has to get those coordinates into those so-called normalized coordinates where everything is between -1 and 1 in your x, y, and z. That has not been an issue for us. Why has it not been an issue for us? Because when we've specified our input geometry, we've always taken care to make sure it's always between -1 and 1. We ourselves have limited our geometry, so we've always been specifying our triangles already in that kind of normalized clip space that we have there. That is not an OpenGL requirement. That's a CPRE 480/580 requirement. This is no longer our requirement. You can now write applications that specify geometry in all sorts of arbitrary ranges, as long as you also provide the transformation matrix that gets it back into that range -1 to 1. That is the fundamental role of a vertex shader. Otherwise, it generally, and if you look at even advanced examples, it's kind of just passing data along, saying, here's my attributes, pass them along to the rasterizer, let the rasterizer generate the data needed for the fragment shader to determine what to do next. And that's what the fragment shader's job is to determine the final output fragment. The fundamental thing it has to do there is determine whether to keep a fragment or not, or determine what that final fragment's attributes, generally its color attributes, are going to be. The inputs are going to be from whatever the rasterizer provides for us, and its output is going to be just the color, as well as we talked about for that depth information, that depth value, that z value to determine should we actually be passing this fragment to the frame buffer or not. The fragment shader doesn't do that operation for us. One can imagine a scenario in which it did, because it can do read and writes and can do branches. You could write it in the fragment shader. Generally, it doesn't do that operation for you, but it passes along and calculates potentially that information for depth so that there's a separate render output module that does that basic input fragment, input position, depth value, determine whether or not that thing should be actually passed or should it be blended into the frame buffer. Otherwise, though, and you can start to see, why this evolution happened so that we had unified shader architecture. Otherwise, while the goal is different in terms of what the programs one writes for fragment shaders, why they would look different than our vertex shaders, not better, not worse, not easier, not harder, but just different in terms of the task that they're doing. Vertex shaders are doing matrix vector multiplication, potentially some per vertex, other per vertex operations here. Matrix vector multiplication is why vertex shading exists. It's why we do that transformation. That's what the code is going to be having. Very common for it to be one line of code. Fragment shaders are where we determine what the fragment's final color is going to be. That could also be a pass-through. If we provided everything is going to be red because this is a red triangle, then there's not a lot of work for the fragment shader to do. It's just going to pass that information on. But otherwise, when we talk about different ways we can calculate what the final color of something should be, that task nowadays falls almost entirely on the fragment shader. We'll look at what happens when you try it in the vertex shader versus the fragment shader, but nowadays it generally happens in the fragment shader. So it's doing generally more work. I think that's a correct statement to make. and it's also being executed per fragment versus per vertex, so the number of invocations of it is generally, for at least the type of scenes we would be handling, a lot higher. 3 vertices could be 3 fragments, but it could also be 3 million fragments, right, depending on the size of our triangle. So there's that fundamental imbalance there. Otherwise, though, if you look at this architecturally, it's almost a copy-paste of the previous vertex shader example there, because it is doing and it's supporting the same exact type of language. There was certainly a time in which the shader languages had real clear demarcations about these instructions are allowed in vertex shaders and these instructions are allowed in fragment shaders, and there's now just very trivial kind of like meta differences between the two in terms of syntactically what you have to provide at the top versus where other things can be placed, but otherwise they're effectively the same in terms of what syntax you can provide, and then architecturally then they're effectively the same. So I've shown different versions of like the big picture GPU architecture as it's evolved over the years, and that was I wouldn't say obvious, I mean it only maybe seems obvious in hindsight, but that was kind of a natural evolution of GPU architecture from the version in which you had a set number of vertex shaders and then a set number of fragment shaders and still kind of a physical pipeline between them, to a version in which everything is just a shader. Sometimes they're running vertex programs and reading in vertex data. Other times they're running fragment programs and reading in fragment data and generating fragment data. But architecturally, why have separate units? They're effectively doing the same exact thing. And looking at this picture compared to this picture, even a couple of the differences I'm listing here are not especially important, because here, for example, it shows the color buffer and depth buffer, but in most modern implementations, that's kind of indirectly accessed. That's a separate module that does that final reading and writing of the color in our depth buffers. I think arguably, although we try to abstract some of that detail away, the most painful part of working with shaders is first off just shader management, right? When you have just one vertex and one fragment shader, there's not a lot to manage there. But in modern video game and engines and in modern applications, you have hundreds to thousands of shaders and various permutations of them for every single effect you want in a game. That's going to be a separate shader that you write. So just managing and working with the different shaders. But even with just one vertex shader and one fragment shader, the OpenGL overhead for it is a little painful, I think, in terms of just the number of functions one has to provide. It's not so different in the different ways. So DirectX's version of this is very similar. Older school CG and other ones are very similar as well. But you have to provide kind of a context, just like we have to do for our buffer objects. You have to provide a context for the program. So there's a call to a function called GL create program. You then have to provide effectively the shader source for your vertex and fragment shaders. That's why there's 2 calls being listed here. We have a program, and again, with one vertex shader and one fragment shader, we'll have just one program. But in theory, you have an arbitrary number of combinations of fragment shaders and vertex shaders. You would have that many different programs potentially in your application. When your game loads up and it says it's compiling your shaders and it's sometimes taking quite a bit of time, that's what it's doing here. For all the different shaders your program may require, create a program associated with them, do the compilation steps, have them ready to go, create the program, you attach the shaders, there's a compile step, and then linking the program together, and then finally, for your draw calls themselves, you have to specify which program you actually want to use here. There was a time in which the aspects of the compilation were entirely up to the driver. To some extent, they still are, but these days we have this spear V, or you can call it SBI or V, that's fine, which is our intermediate binary pseudo-assembly step for our OpenGL shader output. That allows for a certain level of kind of cross-platform compatibility. It allows us to use kind of modern tooling to do modifications and optimizations and analysis of that shader output. And for that reason, that's what our infrastructure does as well. I haven't talked a lot about that. You should be looking at that a little bit in MP3, but those are the steps we kind of follow. We take our GLSL. There's a standard kind of reference compiler. We basically run the reference compiler, which generates this spear V. You can call it a pseudo assembly. You can call it an intermediate. You can call it a virtual machine type language for the same kind of operations. If you have a multiplication operation in your GLSL code, you'll have an assembly-like instruction called mult vector type in your sphere V output. We just take that and convert that to our own assembly that you have in the appendix for MP3. It is generally a one-to-one kind of correspondence because there's no magic there at the end of the day. There's a certain series of operations that the shader language version is expected to support. You need to support these functions, and we'll talk about all the functions as well as the operations. There's the input and output types, and everything is going to be this 4-wide vector. We have this kind of intermediate assembly format. We're effectively operating directly on that. We just created our subset of that, which is here are the operations that you would be expected to support. Sphere V doesn't necessarily say, how one should implement those individual instructions. It just provides that intermediate layer for you to be able to say, okay, here are the type of operations that are required. Here's the loads, here's the stores, here's the additions that we have here. And then it's still up to the driver to determine, how do I take that and translate into something that my particular GPU knows how to handle? But having that kind of relatively commonplace intermediate format is very useful, because then in theory, you could provide your shaders directly as that format. You don't even have to provide the source for your shaders, and the driver just needs to be able to understand this intermediate format to generate the actual binary ones and zeros for the instruction memory for your particular GPU architecture. So you have those series of steps, and many of them then effectively have to be repeated for each of the shader and each type of shader you're going to have in your shader program. So a program must contain, this is an OpenGL requirement, a vertex and a fragment shader. And isn't much else to say other than these are the steps that are required, the number of functions that one has to call. You specify that there's a single program. That's a little bit of a driver bookkeeping. There's a shader associated with the bookkeeping. There's then providing the source. That is the actual text file of the GLSL shader source that you're providing. There's then the compile step. That's going to generate some sort of intermediate representation. Then you have to associate both the thing that you've compiled, attach it to the particular program. Eventually then there's a step where you link all your shaders together. Linking here isn't exactly the same as what you think of as linking in regular compiling applications, where you're using a library and you're checking at compile time that, do I have this function defined in the library that I think I have? Can I find the shared object or the DLL associated with that library? It's not exactly the same, but it's also not that different, because there is an actual checking step that has to happen there, where you have a vertex shader that has certain inputs and has certain outputs, and then you have a fragment shader that has certain inputs and has certain outputs. And until that step, all these operations happen separately and are kind of independent from each other. You compile your vertex shader, you compile your fragment shader. The linking there is not, again, linking in terms of generating a single binary or anything like that, but it's checking to see, do the vertex shader and the fragment shader you created, do they make sense together? Do the outputs of your vertex shader correspond to the inputs of your fragment shader? If not in name, which is how it used to have to be, in number and in relative position of the input and output attributes. Because otherwise it's just not going to work. What does it mean to have a vertex shader that generates one output and a fragment shader that expects 3 inputs? Logically, it doesn't mesh, right? I mean, the rasterizer is generating something, but then the fragment shader wouldn't have the data it needs to actually continue its operation. That's the step that happens here in GL-Link program. Likely, the errors you will see will be in this stage, because again, syntactically, when we do compile shader, there isn't all that much going on that you can't handle, right? It's very basic C-like code at that stage. Sure, Ben?
So when you attach a shader, is that just telling it, hey, you need to link this?
Yeah, I keep calling it kind of metadata, or bookkeeping is what I call it. If you look at our driver's implementation, which you didn't have to write that code yourself for our OpenGL implementation of GL attached shader, it's saying, take the binary blob we generated here and associate it with this program object. So it's not really doing much, just saying, hey, when it's time to run this program, this will be the binary blobs we're going to be making sure we're copying over. I believe for our implementation, although again, this is not a requirement, this is just our implementation choice. although you have to look at the driver code for MP3 anyway, I think we wait until GL use program to actually copy the stuff over and get the actual instruction memory copied into our DRAM. It could be done earlier, and then GL use program could be then just setting a program counter. You could do it either way. Our approach isn't strictly correct in that if your application had many different programs it was running, many different shader programs it was running, that wouldn't be quite correct. But we're always limiting ourselves right now to one program per application, per hardware. There's nothing wrong with our implementation that would prevent you from having two different shader programs. One was enough. I don't know. One seemed like enough to kind of get going, and the rest is really just bookkeeping. So keeping track of your pointers both in your driver memory and in your GPU device memory, making sure that like you're flushing appropriate caches, making sure you're setting the program counters to the right value. We just check GL use program and say copy it over. And even if you then call GL use program multiple times, I think it just checks and say, oh, we already copied it over. We don't have to copy it over again. So most of these, in my opinion, are bookkeeping functions. GL create program sounds like it's doing something impressive, at least in our implementation. In my understanding of the Red Book and how one would have to implement this and how we built it, just say we have a program object, whatever you need to store there. Likewise for creating shader. Shader source is just text processing. Give me a car array of what my shader source needs to be. That's all that's doing there. Then you have to read from a text file if you need it there. But you can just provide it as a big string. It doesn't need to be provided as anything other than that. Compile shader is where you're doing, I would call it GLSL syntax checking and generating that intermediate output. Again, for us, that could be really complicated if we had to build that entirely from scratch, but there's reference compilers that we just use. So GL slang is the reference GLSL compiler, and we just use it, and it works, and it generates that SPIR-V output. Where for us it gets a little then tricky then is at that point where when we actually want to generate our output, which is the simple graphics processor ISA output, that requires a separate translation step. You can't directly take the SPIR-V output, at least not trivially so, and build a processor out of it. It wasn't meant for that. It's a pseudo assembly. It's this VM type level of you know LLVM. It's effectively the same exact thing as what LLVM intermediate representation generates. You generally are meant to take that and then actually translate that to the final binary blob corresponding to your program, and that's what we do there. Why did we write it in Lua? The guy who helped me with it really liked Lua. I don't know. Has anyone looked at the Lua assembly for the compiler yet? You don't need to until something doesn't work or you want to add your own instructions. I didn't play around. I've never played around with Lua before, but it's source. You look at it, you can figure out what it's doing. It's a different syntax. It couples very nicely to C, so you can directly call the Lua interpreter and get your result. But that's the extra step that we then have to add, that your actual NVIDIA or AMD driver has to add. When you call this, sure, you can get this kind of common intermediate representation. What does that mean for your system is what then your driver then has to determine. And then use program is get started. That's what I would call GL use program. It could be as simple as just setting a program counter for both your vertex and your fragment shaders. We have been running these functions all semester long, but we've been kind of wrapping them in a higher level call that kind of, everyone does it. It's not like we're doing something kind of weird, just a piece of functionality in our driver code called load shaders. But you look at load shaders, it is doing everything up to the call to GL use program. It calls create program, create shader, shader source, compile shader, attach shader, link program. That's basically all that it's doing. Plus some text utilities so that you can provide it just a file name and it just reads the file. So some little text IO utilities. But that's what that is doing. So every step along the way, we're actually calling all of those. We've been calling all of those functions along the way. So it's maybe the most annoying part of working with GLSL, but it tends to get extracted away. For us, that's sufficient because we always just have one vertex shader and one fragment shader working with a proper game engine, a more advanced simulation or render you may be interested in. Managing your combination of vertex fragment shaders is a non-trivial task, and because we're talking thousands of shaders, any individual effect. This tree looks nice. This sword looks nice. This little light shining through. Those are all different shader combinations. And managing that is what game engines are meant to be there to help you do. There's separate resource management engines for that as well. For us, that could be complicated. We've kind of kept ourselves limited by saying one vertex, one fragment. That's it. If you want to, you can probably get it to work, but that could be for your project. If there's some effect you really want to show that requires 2 shaders, have at it. You should be able to do it. It's just not tested. There's no MP assignment that requires that you do that. Let's do our first GLSL shader, although I know you have them. This one is fine. This is our basic transformation into clip space shader here. Let's do an even more basic one. First off, that one's kind of hard to read. Let's look at our shapeshifter program, the very first MP3 program here. Let's actually, I was going to actually bring it up to actually run it. It is otherwise, in terms of the OpenGL program, and I want you to take a look at that when you open it up, it should be essentially identical to the red triangle. Well, that doesn't look especially red, does it? Fine, we'll figure it out. We may have already looked at this. I may have broken something earlier. But in terms of what setting up the window, specifying your geometry, I think I intentionally made smaller triangles because we're shifting it and we're not doing clipping, so I didn't want it to like shift and become larger so that it doesn't fit on the screen anymore. But you can play around with that as well. The one difference would be it's running a different vertex shader. That's the whole point we're trying to expose here. And then it's doing this kind of shader plumbing that is critical for us as well. I may not be covering this in the exact order that I have the slides, but let's talk about what's happening with these 4 lines of code, because from the driver perspective, you need to be aware of this, and then architecturally, this has implications as well. I have here the actual vertex shifter shader that you're running for that MP3 application. Couple things. Let's just go through it line by line, and then we'll talk about more advanced features later. The version matters quite a bit. I've talked about how we're supporting OpenGL version 3.2-ish. It really depends on what shader features we got to work and which ones we didn't get to work. What this feature provides, which is important for how we implemented things, is specifically specifying our input attributes and the requirement that we specify the relative location of those input attributes. And we have to do that, and we needed that for our implementation. This code will not work in your hardware if you change any of those. You can change the variable name, but if you change anything else about those 2 lines. Because our hardware, as we've talked about, has a physical FIFO as our input to our vertex shader. And it has 4 attributes. First one, or location 0, is always going to be position. The next one's always going to be color. The third one's always going to be texture coordinate. The fourth is up to you to use if you have some other need. Vertex normals is a common thing to use for that 4th one. If you need a 5th one, you have a lot of work ahead of you. The FIFO is 4 entries wide, and that's all we got. So we are specifying our inputs here, and the keyword here would be in. Right? This is an input attribute to my vertex shader. We specify vec3, but if I did vec4, this wouldn't change the emitted code. Things are going to get promoted to vec4s here. And we're specifying specifically relative to my vertex attributes that are coming in, which one am I? Literally, which offset am I from this big array that's coming in? I'm the 0th attribute. It's the first 4 entries corresponding to our XYZW, the next 4 entries corresponding to our RGBA. And then we have output, where for this, unless you're going to have multiple output, it just starts with a couple of assumptions. So let's go through our end result. Is we have 2 outputs here. This also depends on which version of OpenGL you are looking at. But in this version that we're using, version 3.2-ish, every vertex shader has to generate an output attribute called GL position. That's just a requirement. Later versions, you have to still generate a position, but you can call it whatever you want, and you can give it an appropriate name and location. In this case, this is just the requirement of this generation of OpenGL. There is an undeclared output value, effectively called this. And not only that, it would be the actual syntax for it, if it worked, would be something like that. And every vertex shader has that kind of hidden line at the beginning of it. You can think of the requirement that way. So no matter what, you're specifying that. Every other attribute you specify as an output is going to be relative to that. We then have these 4 uniforms. I don't really like the word, but the previous words weren't necessarily great either. They were just calling them constants when they really weren't constants either. Uniform means constant for that entire frame, right? Does not change per vertex. So all the vertices I specify, there's only 3 in this case, but if it was 3 million, it wouldn't matter. They're all going to get different values potentially for this, but they're going to get the same values for these 4 scalar float values that we're specifying. The idea there is you have a frame, you're rendering it, you then want to change the frame for the next one. This is the way you get some dynamism in your scene without changing your geometry at all. We've had stuff that's moved before, right? We get stuff that moves by setting our geometry, our vertices, our GL array buffers, and then changing them. Draw it, clear the screen, draw a whole bunch of new ones. Draw it, clear the screen, draw a whole bunch of new ones. This code, which is moving as we saw here, doesn't change. It's always the same 3 vertex positions. Our attributes do not change. If it's 3, what's the big deal? But if it's 3 million, that's a pretty big deal, right? Our geometry has not changed at all. We're not having to copy any more data over to the GPU memory. We've specified it once. Maybe later we change it, but for now we don't have to change it. Our input scene does not change. What we then have are various per frame or per scene variables that we then specify separately in our program. There's a couple different ways to do it. One such way is you query your GLSL program for the name of a uniform, and you do it by name. You can also do it by position. This is a very common way of doing it, where I'm specifying the function in OpenGL is GL get uniform location, the program ID that we did from GL create program, and the name of the variable in my GLSL code. Give me the offset IDs, some driver-specific ID. I think we just start at 0 and increment them. I think actually what we do, you'll have to look at it yourself. It's been a little while since I've looked at that piece of code, is we check what the driver returns and just copy that value. Because we don't care. We just need them to be different values. We don't actually care what the actual value is. For those 4 things, the expectation is you have those 4 variables defined as uniforms in your code. So give me a handle, give me an ID. It's not exactly a pointer, but it's kind of like give me a pointer to those uniforms. And then when it comes time to actually do the setting of those values, there are a series of not really object-oriented kind of function calls for the different data types we have to support to set the value of the offset ID of whatever variable I have in my OpenGL program for the current value of X offset, Y offset, X scale, and Y scale. So in my main render loop, I'm just calling GL clear, GL draw arrays, and swap buffers at the end of the frame. Clear, draw arrays, clear, draw arrays. The only thing that's changing is a little bit of silliness of, this is an arbitrary function. This is all running on the host side, on the CPU side of calculate a value for X offset, Y offset, X scale, and Y scale. Make sure it doesn't get too small or too big. And set the uniforms accordingly based on what we just calculated for those 4 values. Set these 4 inputs to my shader program for the vertex shader. What does our code then do here? Takes our input vertex position, just copies it to a local variable, and it modifies the positions X and Y based on multiplying by a scaling constant and by adding a scalar offset in the X and Y dimension here, and then sets our final value here. Why is my color white, though, for this example? Should be red. When in doubt, compile it again, I'm sure there's a reason. And that's why you're seeing that the geometry hasn't changed. I'll figure out the color. Give me a minute. The geometry hasn't changed, right? The actual attributes we've passed to hardware for X, Y, Z are always just these. It should just be a small little triangle along the way. And in fact, without changing our OpenGL program at all, if we just got rid of this, I guess the best way to do that would be, I just gotta remember to change that back before I confuse myself next time. I did all this math, but don't even use it. Just give me my input position, copy it from, make it a pass-through shader, again, as it was before. Without recompiling our program or anything, we're loading that shader. Now it should be a very boring kind of static triangle, right? Give me a little compile error. Assignment of incompatible types. Let's take a look. We would have to open the pass-through fragment shader. Input vector v color f. There's nothing wrong there. Vertex shifter. Output vector for v color. Does it give me that warning when I run it? I didn't change anything.
So just so I understand what it.
No, I can't explain why the color just came back on. What did I change anything? I was trying to show the position not changing. So it's giving me an error because, okay, assignment of incompatible types. Yeah, so I would have to do like vec4 of, you're right. So it seems okay, but yeah, I would just have to comment out those lines, and then it shouldn't give me incompatibility. So that, we have our nice color shifting triangle. This is what you should be seeing at the end of your MP3 simulation for that. Some of the just basics of the types that you have to support. Again, generally everything's a float unless you specify otherwise. I think it's a nice feature of the language and the general class of languages that you do have vectorized and matrix types that are kind of just built into the language. If you have been playing around with the GLM library yet for MP3, it provides a very similar C++ interface. It is basically meant to be an equivalent kind of byte by byte matching of what you can do in your GLSL syntax, just in your application program itself. If we go to the second application of our cube flyby, you have to read the documentation to really grok exactly what's happening there, but it basically provides the same kind of data types of GLM vec3 and GLM mat4, and it lets you do things that otherwise would be a lot of just error-prone C code of multiply two matrices together, just using that operator. It overloads the operator to allow us to multiply those things together here. There's no coincidence there. So GLM was created to kind of be compatible with the shaders that we would be writing. It provides the same kind of functions that used to be available in fixed function OpenGL, and now we have to kind of manually do ourselves. If you use this library, you can still use those kind of things, those functions that allow you just to say, set my camera here and have it look at this direction with this particular type of lens or this type of perspective, and just calculate all that all at once. But just generally, it's a nice feature of the language that you have these vector types. You can access them as if they are arrays. It's much more common in your shader code to access them as the individual subcomponents operator. So we have our actual constants. We have our uniforms, which are changed between individual frames. We have our inputs and our outputs. You can actually tell whether or not we actually want the rasterizer to do interpolation or not for your output vertex attributes. We don't support that. So our rasterizer takes vertices and does interpolation of them. So if you try, no perspective would look fine, but if you try flat, which is basically saying, don't do any interpolation of this, treat all the values of having the same attribute, that won't work for us. Our rasterizer interpolates everything. And then there's just memory regions that potentially they have read and write access to as well. Otherwise, the operator you should feel very comfortable working with GLSL code. Again, when you have a syntax error, our tooling may not be the best at giving you helpful feedback for those syntax errors. Those would be good questions to post, like in the class, Discord, about okay, I wanted to change this shader and I'm getting this error. There's other either web utilities or you can just directly run the GLSL validator yourself to get more user-friendly errors. We generally just collect those errors and don't try to provide any meaning to them. And so, like that linker error, that was the correct error. But if you didn't know what to look for, you could spend some time on that, right? So you did catch that. We were connecting a vec3 to a vec4. You have to do the padding. But otherwise, for other kind of syntax errors, you're pretty safe working with just C-type code here. You just have to be a little bit careful along the way here. You've already seen then these examples of these kind of built-in initializers / constructors where you can then specify a vec3 or a vec2 or a vec4. I think a fair way to say it would be if you wish that feature was available to initialize a vector type in GLSL, it generally is. Like, it generally does everything you would hope in terms of composition of these scalars and vectors into larger vectors and matrices as well. It's not necessarily a trivial thing to provide, right? So here we initialize a vec2, we call it my YZ, and then we want to initialize a vec4 called my position. We specify it as a vec4, we specify a scalar, this vec2, and then another scalar, and it just kind of works. It gives you exactly, I think, what you would hope that it would be able to do for that. Then there's the swizzle operators. First off, you specify the components you're interested in. You can specify between 1, 2, 3, and 4 of those components at any given time. This is where you'll get syntax errors if you do this incorrectly. Depending on the context for the data, the different component selection operators may be more or less meaningful for you, but they are equivalent. And this is can be a little tricky, and they're interchangeable, and the compiler takes care of all that, including the front end. We don't take care of that. The GLSL compiler takes care of that for us. But if you have a vec4, you can access it as .x, .y, .z, .w. I know you're all itching to learn about perspective. We'll get there. Or you can specify it as .r, .g, .b, .a, or specify it as .s, .t, .p, .q, and we'll talk about that. That's for texture coordinates, but they're interchangeable. They have only the meaning that you as the programmer impart to them. .x is always, block offset 0, right? It's the first entry in that vector. .y is always the next one. .z is always the next one. Same with .r. So my value .x is equivalent in all ways, shapes, and form except for programmer intention with my value .r, and it's equivalent to my value .s. It would seem to make sense to me that when you're dealing with positional data, you would want to do .x, y, z, w. That's what it's for, but you're not required to. I'm always a little leery of changing things without actually checking, but in fact, I changed the wrong one in there. But in fact, this would be valid code. Okay, I've said that. I'm going to run it, and if it fails, I'm going to pretend that it was all intentional. Yeah, okay, it does work. It's valid code. It seems kind of nonsensical, I think, arguably, that I'm taking my position value and I'm taking the red channel of my position value, right? It doesn't seem to make much sense. Likewise, we did this vector of color, and we could have done it with the individual scalars. Let's do it in the right order. It's red, so it doesn't matter, but let's do it in the right order. And in theory, and I could just do it all at once here. I could do color.xyz. That seems weird, right? Like, why am I taking color of xyz? But it should still be the same. If I do, how about xyx? Here's some of the power of the swizzle operator. What color is that triangle going to be? There you go. Okay, at least you were thinking about it, and I appreciate it. It should be whatever that literally bright purple would be. I don't know if our color channel was entirely red or if it was. Yeah, it was 100% red. Arguably nonsensical, but that's all the swizzle operators are providing for you. They're providing this individual component instantiation or selection operator, and then basically all the possible permutations of that. If I wanted to reverse things, I could do .wzyx as opposed to initially it would come in as .xyzw. and any of those possibilities are valid. And so that unit you're having to build, it's not as bad as it could seem, but it's just the individual piecewise selection operator. For my 4 outputs, I'm looking at my 4 inputs, and for each of these components in term, and there's only 4 of them, you only need 2 bits, right, to represent each one. It's basically a mux for each one. For any of my 4 inputs, could independently be any of my 4 outputs. So 4 series of muxes is probably going to be sufficient for implementing that. But I think conceptually wrapping around your head is like, why would I want to ever do .xx, .yy? There's reasons that would, for certain kind of simplification of the math involved, you'd want to do that if you want to keep things in a vec4. In this case, I could do position.r or position.s, as we saw as the other example. Usually, though, from the programmer's intentions perspective, you want to keep the swizzle operators to what is relevant for the data that you're actually working on. You can do color.xyz, but why? Why would you actually want to do that? Any questions about swizzle operators? I think the assembly syntax is a little tricky for it because there's just a lot of permutations you have to be able to support, and then conceptually it's a little bit different as well.
Where's the name come from? Why is it called swizzle?
I had looked it up at some point and I don't remember. It's a swizzle, right? Swap. It's got a name, and it's an old school graphic kind of name, like the what was the other one? The blitter operator we were talking about the other day. You have to report back to class on Thursday about what you've learned about swizzle etymology. There's basic flow control, so you can have for loops. The tricky part about talking about flow control with shader language is it's so version dependent what limitations there are. My recommendation is for your programs that you're working on for MP3 and beyond is not to do any kind of flow control. We don't have much in the way of branch operators and things like that. Just stick with just straight line code. You can make a lot of incredible effects without having any flow control whatsoever in your shaders. You can have function calls as well. We should be able to support that, but I haven't tested it. There's a lot of these, built-in functions that easy, I think, is a valid thing to say. Fast is kind of assumed that the language supports them natively as built-in operators, built-in functions, and the assumption is generally those are going to get mapped to a single shader instruction, that there isn't a whole separate level of microcode associated with it. So calling sign of x in your shader code, I think, is fundamentally different than calling the sign function in your math library. Math library is also optimized, but it's an optimized piece of software that may be architecture specific, but otherwise is trying to do the best it can at giving you a good, fast version of sign of x. Generally, if you have a built-in native support for a function, trigonometric or otherwise, it should be assumed to be generally that there's a single shader instruction, and it should be a relatively fast implementation of that single shader instruction. Otherwise, beyond kind of the headaches of compiling and linking and making sure that you've done the little kind of meta programming correctly here, generally a shader language is kind of a joy to work with. Things that would be many, many lines of C code, and with the right Python library is also very straightforward, but otherwise can be a real pain to work with. Just kind of work with regards to working with these vectors. Your matrix, your matrix vector, your vector matrix, component-wise or doing the entire thing at once, all just kind of work the way you would hope that they would work. And then similarly, anything related to modern computer graphics and the mathematical operations required of them. And it does get kind of mathy at some point when you look at sine distance functions and calculating normals and things like that are all kind of natively supported in the shader language. You don't have to build up really anything yourself from scratch. So it's a joy to work with for that reason, and can generally assume to be reasonably efficient to use those functions. Finding the actual details is a little tricky, I think. The CUDA documentation, which is not for real-time graphics, but is using the same exact hardware, attempts to document some of those things. So if you look at the CUDA documentation, it'll say there's an inverse square root function, and it takes 16 cycles. So that's just something to know. Is 16 cycles a lot? Is it not a lot? It's hard to say, right? It depends on what you're actually using it for. But you can find some of the information via that kind of documentation. Inverse square root's an interesting one. It's actually quite important for doing lighting calculations. So we are not expecting you to support square root or inverse square root for MP3. Those instructions are marked with an asterisk because they're just hard. They're a project in and of themselves. If you're taking like a VLSI like EE465 or something, building an inverse square root operator is a good class project for that class. That's enough work to be done there. You don't have to add it onto your MP3 workload here. It's kind of an interesting one, just historically. This will be the last thing we talk about here today. Inverse square root is needed for lighting calculation, and there's of course like an academic paper on it, but then the Wikipedia, as with many academic articles, the Wikipedia entry is a little bit better for understanding the concept. In the original, I think it was the Quake source code, there was an implementation of inverse square root. This was before shaders. This was, there was no shader code. This was running C code on the workstation on the CPU, and it's something that had to be done quite commonly. So getting it done as quickly as possible was very important. Your Intel hardware may today support inverse square root. It may not, and there's either a library call that's somewhat fast, but not nearly fast enough if you're doing this over and over again. Somewhat academic article. I would argue the Wikipedia article is a little bit better. So this is your other quick little homework, is to look up fast inverse square root, which is exactly what it sounds like, calculating 1 over square root of x, which is very common for lighting calculations. The article is great for a couple reasons, because it talks about like why you need to do it, and we will be talking about this when we talk about lighting calculations. We get there late in the semester because it's not super critical for your labs, and we can get to it eventually, but why the calculation is necessary. And here is John Carmack's code for how he implemented inverse square root. And it's incredible. I mean, some programmers are just more clever than others, and he's been interviewing Clay. No, he didn't invent this, and then someone else at the team, but it goes back way back, so it's not really clear who exactly invented this. But it starts with a completely magic number, and those comments are in the original source code as well, and does one iteration of effectively Newton's method to give a reasonably sufficiently accurate estimate of the inverse square root of an input floating point number. So you can Google and find this Wikipedia article, or you can find this article pretty quickly. It's fast inverse square root. It's not super relevant for us. If you were to implement this, I think it would actually be harder for us than it is for them. If we were doing floating point hardware, you'd be fine. With our fixed point hardware, this hack doesn't work at all. It involves an assumption about the IEEE 754 representation of floating point that that value is relatively close to the square root of 2 and can be a good starting point for floating point values in a certain range. So if you're interested in this kind of thing, I don't know if I can do it justice, certainly not in the next couple of minutes here. Take a look at this. If you want, if you read it between now and Thursday, let's discuss this on Thursday. But okay, now it's a single instruction, so somebody implemented that very efficiently at NVIDIA. But it's kind of cool to see what you can do with limited resources, right? And how one can play around with the data representation, doing just a very small amount of actual math here. When we say fast, we mean incredibly fast here, right? Floating point, constant multiplication. The rest are just basic arithmetic and shift operations, shift and logical operations here, to get what would otherwise be a very complicated operation done in probably fewer than 16 cycles in modern hardware as well. Let's leave things here for today. Want to see how things go tomorrow, but that's my best guess that next Tuesday will be our demo day for MP3, and everyone should be efforting towards that. Again, there's no point in a demo day if everyone's just showing black screen and compiler errors and frustration. That's not the point of this class. So put good faith effort into it tomorrow, work on it beyond tomorrow, work with the TA, post questions, get stuff done. Tuesday, I think, is very reasonable. I think we can all get it done for next Tuesday. So good luck. I'll see everyone tomorrow in lab, and enjoy.